So let me remind you both things. Let me start with the graph of the function 2 to the power x. The graph was as follows. When x is equal to 0, 2 to the power 0 is 1. Right. And then for every step to the right that we take, the function doubles. Every step to the left, well, you should divide the value of the function by 2. So at 1 is 2, and grows very fast to the right, in the case rather fast to the left. So it was something like this. This would be 2 to the power x. Let's say I want to draw the function, let's say g of x is 3 to the power x on the same graph. How would it look like?
Start at the same line.
Okay, so it also passes through this point. When x is equal to 0, 3 to the power 0 is still 1. In fact, any number to the power 0 is 1. Then, what should I draw?
It grows at a faster rate.
Right. So something very similar, but it will grow at a faster rate. For every step to the right that we take here, the function will triple. So at 1 it is already 3. At 2 it's already 9, so probably somewhere off the board. To the left, what happens? If I go to the left, does it decay faster or slower than this? Faster, yes. So every step to the left I'm taking, the value of the function now gets divided by 3 instead of by 2. So it is decaying even faster. So that would be 3 to the power x. Just for the fun of it, let's take this function, 1/2 to the power x. What can I do? Well, how does the graph of this function look like? Yeah.
It starts there as you get more positive, it actually gets smaller.
Okay. So this function actually decays as we go to the right. For every step to the right I'm taking, the value of the function gets multiplied by 1/2. So this function decays as we go to the right, and vice versa. As I go to the left, I will divide the value of the function by 1/2, which is the same as multiplying it by 2. So it will grow as I go to the left. So this will be 1/2 to the power x. In fact, you see this graph 1/2 to the power x and 2 to the power x, they look somewhat similar. And there is a reason, of course. I can write 1/2 as 2 to the power -1. That's 1/2. And then this thing is 2 to the power -x. We seen last time that if you take a number raised to the power m and then raise the result to the power n, it's the same as raising the number to the power m times n. So here I raise it to the power -1 then x, same as raising it to the power -x. So in fact, this graph and this graph should be just reflections of each other in the y-axis. And they are. Alright, so these are graphs of different exponential functions, a number raised to some power. Last time we also started talking about derivatives of such functions. So with our first function, f prime of x, remember that the derivative is given by this expression. And in our case it was like this. 2 raised to the power x plus h minus 2 to the power x divided by h. That is the limit. Next, we apply the rule for a number raised to a sum of two numbers. So here we'll write this as 2 to the power x times 2 to the power h minus 2 to the power x divided by h. Next, I will take this 2 to the power x out. I'll factor it out. So it will be limit as h goes to 0, 2 to the power x times 2 to the h minus 1 over h. And next important step was to notice that 2 to the power x does not depend on h. You can take any h, you can change h as much as you want. 2 to the power x is not going to change. So 2 to the x does not participate in this limiting procedure. I can take it out. And then I'm left with such an expression. 2 to the power x times this limit. And in the very end of last time, I told you that this limit, 2 to the power h minus 1 divided by h, well, this is a complicated limit. There is no question about it. It's a very complicated limit. But it is some number. However complicated, it is some number. So, limit as h goes to 0, 2 to the power h minus 1 divided by h. Well, you can approximate this by just plugging in really small numbers h inside this function. And if you do, you'll find that this is approximately 693 something. So this is because 2 to the power 0.001 minus 1 divided by 0.0001 is approximately 0.693. And similarly, if you plug in other small numbers instead of h, you will also get values close to 0.693. So this limit is, well, some number whose decimal extension starts with 693. It in fact goes on and on and on and on. It is not a rational number, but it is some number. And the result was like this. The derivative of 2 to the power x was this number, 693 something something, times the function itself. Well, nice result. Derivative of this function is a number times 2 to the power x. Well, let's explore other exponential functions. Why are we using 2 to the power x? Let's use just some number c to the power x. How will it change the result? Well, here's how. Similarly, if you take any number raised to the power x and find its derivative, the derivative of this function, like, let's say, 3 to the power x, you can go over these steps exactly, just replace the number 2 by the number c. And then you'll get the following. It's the limit as h goes to 0 of c to the power h minus 1 divided by h times c to the power x. So basically the same computation and the same answer, except instead of 2, I have c. So for this function, we also have the result that its derivative is some number times c to the power x. Okay. But once again, we have this complicated limit. For example, derivative of 3 to the power x is limit as h approaches 0 of this thing times 3 to the power x, and limit as h approaches 0 plus 3 to the power h minus 1 divided by h is, well, once again, you can use similar technique. Plug in small numbers and find out what this limit is. Turns out it's about 1.098 and some other numbers afterwards. So once again, the reason is because if you raise it to some really, really small power and divide by this power, you'll get a number which is 1.098 and some other digits. So next question is, all right, so for different values of c, you'll get different functions which satisfy the following. The derivative of this function is this number times the function itself. Next question is there some number for which this thing is exactly 1? It would be really fun to have a function whose derivative is exactly the same as the function itself. We have a whole class of functions for which the derivative is some number times the function. Is there one of those for which this number is just 1? It would be really convenient. Well, for 2 to the power x, this number was a little bit smaller than 1. For this one, for 3 to the power x, it's already a little bit more than 1. Well, conceivably there should be a number for which it is equal to 1. So let's pretend that there is a number like this. You'll find it quite soon. But for now, we'll say like this. Let E be a number such that limit as h goes to 0 of e to the power h minus 1 divided by h is actually equal to 1. So this multiplier is actually equal to 1. For such a number, the derivative of the function e to the power x would be 1 times e to the power x. So for now, I just have a number of which I'm not even sure that it exists. I'll convince you in a second that it actually does exist, and I'll tell you how to find its exact value. But for now, I'm just saying that let's pretend that there is such a number for which this limit is equal to 1. If it has such a number, then the derivative of this number raised to the power x is the same as the function itself, e to the power x. So for now, I define this number rather implicitly. It is such a number for which this limit is equal to 1. It doesn't even tell you for sure that there is such a number, or if it is, whether it is just one such number. Maybe there are tens and thousands of such numbers, infinitely many such numbers. I don't know. So the next question is, can we find this number? Is it, well, I don't know, something closer to 2, something closer to 3, something closer to 1,000? How to find this number? Let's find P. Well, I'll start with this implicit definition. If I want e to the power h divided by h as h goes to 0 to be 1, if I want this limit to be equal to 1, it is the same as saying that for small h, e to the power h minus 1 divided by h is approximately 1. That's exactly what the limit means. It means that as h becomes smaller and smaller, this expression becomes closer and closer to 1. Well, let me rewrite this. i.e. e to the power h minus 1 is approximately equal to h. Or in other words, e to the power h is approximately 1 plus h. Well, this gives you a way to find what e is. E is approximately 1 plus h raised to power 1 over h. So if you take the h, root of power h of both sides, you'll get this thing. In fact, since this approximation gets better and better as h gets smaller and smaller, here we have a precise way to find what e actually is. E is the limit as h goes to 0 of 1 plus h raised to power h. What is this number? This limit is now something, 1 over h. Please note the correction here. It's raised to the power 1 over h. So what is this number? Well, using this limit, you can find at least approximations to this number. E, let's say, is approximately equal to some small number h, let's say 0.0001. 1 plus 0.0001 raised to the power 1 divided by 0.0001. So it is and if you find, well, if you compute what this thing is, multiply 1.0001 by 10,000 times, you'll find that this is 2.718 something else. So in fact, we have an actual number. Some number, it's not a simple number. 2.718 to 8, and the expansion goes on and on and on. What's interesting about this number? Well, it is a complicated number. It's not a rational number, not a fraction, not 2, not 3, something like this. Complicated number. What's interesting about this number is the following. The derivative of the function e to the power x is e to the power x. So here are, let's say, 3 important things to remember about this number e. One is this. We have a way to actually compute what this number e is. It's the limit of this expression as h goes to 0. We'll use it later as well. So this is one thing to remember. We actually have a way to compute this number e. If we do compute it, we get something like this. E is approximately 2.7, or if you want more precision, 2.71. If you want lots of precision, 2.71828, then gets 1828906090. So it is some number. And finally, the most important fact about this number is that it helps you solve this question. Find a function whose derivative is actually equal to the function itself. That's the function, e to the power x. let me sketch the graph of this function e to the power x. Well, e to the power 0, like for any number, what is it? 1, yes. So here is 1. This function is, after all, just a function like a number raised to the power x. In fact, it's some number, so somewhat like 3 to the power x. Or more precisely, something like 2.71 to the power x. So for every step to the right that you are taking, the value of this function will get multiplied by 2.71 approximately, by this number. Well, that's interesting, but doesn't allow you to draw a graph that is quite precise. So you know that the general shape of this graph would be something like this, like it was for 2 to the power x, like it was for 3 to the power x. But here's much more precise way to distinguish this graph from graphs of other functions, like 2 to the power x, like 3 to the power x. Think about what is the slope of the tangent line to this graph at the point 0. So slope of tangent to lines e to the power x at x equal to 0. What is it? 1, yes. So in general, the slope of the tangent at point x is the derivative. The derivative of e to the power x is e to the power x. So the derivative of e to the power x at the point 0 is e to the power 0, which is 1. So in fact, here, if I draw a line of slope 1, let me erase this. First, draw a line of slope 1. That's really easy to draw. And then I'll have to find a graph of exponentially increasing function, which is tangent to this line. So this is going to be e to the power x. And this is not equal to 1 plus x. And if you are curious about how this e to the power x can be compared to 3 to the power x or 2 to the power x, well, e is somewhere between 2 and 3. So 2 to the power x grows slower. 3 to the power x. 3 to the power x grows faster. So it would be like this. 3 to the power x. And e to the power x is somewhere in between. What's special about it is tangent to this graph y is equal to x plus 1. This graph became two graphs, so we can remove those. They're not as important. So, these are questions about this number e. Or the graph of e to the power x, or whatever. One of the things that we discussed. So we found one function for which the derivative is actually equal to this function. Now it makes me curious, are there other such functions? Is it the only such function, or maybe there are many more which after all, I just started with some function of form c to the power x, I found its derivative, it turned out that for some particular value of c, the derivative was the function itself. But there are, of course, much more functions than just functions of the form c to the power x. Are there some other functions for which the derivative is the function itself? Well, let's find out. So, question. Are there other functions for which f prime of x is equal to f of x? Before we go on and discuss the essence of the question, let me first throw in a smart word. Such a question is called a differential equation. So when you ask a question, are there any functions which satisfy some kind of equation which involves the function itself, its derivative, maybe its second derivative, third derivative. So a function and its derivative. Such a question is called a differential equation. And it turns out that such questions are ubiquitous every time you model processes in physics, continuous processes in physics, in economics. It turns out that in many domains of science, naturally, questions can be reformulated mathematically as some relationships between some quantity and its derivatives. So it turns out that knowing how to answer such questions of this type is extremely important for scientists. In this course, we'll only deal basically with, maybe in the second term, we'll deal with more complicated differential equations. This term will definitely see only this one, but in general, there are special courses, like in mathematics, it will be a second year course, which just deal with different differential equations. So it's a complicated and very rich topic. But for now, let's just discuss this particular question. Are there functions for which the derivative is equal to the function itself, except for the function e to the power x? So does anyone see another function? Give you a hint. Start with the function e to the power x and produce function which is not quite e to the power x, but which still will satisfy this equation. So something very much related to e to the power x, but not quite. Okay. Another hint. What will happen to the derivative of the function if I multiply this function by 5?
Would it be similar?
Okay, it would be the same thing, but multiplied by 5. So if I take, let's say, function e to the power x and multiply it by 5, the right-hand side will get multiplied by 5, left-hand side will get multiplied by 5, so equality will remain inequality. So, first some guesses. E to the power x works. 5 times e to the power x also works. If you take derivative of this, it is 5 times derivative of that, which is 5 times e to the power x. Well, this generalizes. If I take any number and multiply it by e to the power x, it's also going to work. Well, if you try and try and try and try, you see that it's hard to come up with other examples of functions for which this also works. maybe after a while, you get convinced that these are the only examples that are going to work. Let's now prove it. So now, solution of this question. Well, suppose I do have a solution of this equation. Some function for which the derivative is equal to the function itself. First trick, I suspect that this function is going to be of the form a number times e to the power x. So let me create a simpler function, or supposedly simpler function. Let me just take this f of x and divide it by e to the power x. So I'm creating a new function, which is my old function, but now divided by e to the power x. Well, why am I doing this thing? Somewhere in the back of my mind, I have the idea that eventually I want to prove that this function f is in fact a number times e to the power x. And that would be the same as trying to prove that this function is in fact just constant, not changing, not depend on x. So maybe it's a smart thing to consider this function instead. Well, okay, so the first question. Here I divide by something. It might happen that this new function is not defined at some points, namely at the points where I divide by 0. Can it happen? Is this function actually not defined at some points?
No,
Why?
because no matter how small e is, even if it's a negative number, it's never going to approach 0, because you can't really raise anything to a power. It doesn't make sense.
Okay, yes. So in fact, e to any power is never equal to 0. No matter what the power is, large or small, if you take a non-zero number and multiply it by itself any number of times, or raise it basically to any power, you're never going to get 0. So g of x is defined for all x because e to the power x is not equal to 0 for any x. Please also remember this step. It is something to have in the background. So you should know that e raised to any power is never equal to 0. Similarly for hood raised to any power, or 1/2 raised to any power. If you take a non-zero number and raise it to any power, you are never going to get 0. Okay, so this function is defined. What is so special about this function? Well, conceivably we know something special about the function f, which involves its derivative. So let's compute the derivative of g. What is derivative of g? Well, it's derivative of this thing, f of x divided by e to the power x. How to find this?
The top prime times by the bottom.
Okay,
Minus.
quotient rule.
Yeah.
So this thing is a quotient of the functions for which you know the derivatives. So it's like this: f prime x times e to the power x minus f of x times e to x prime divided by e to x squared. Now I will use my knowledge of the derivatives. F prime of x is in fact f of x. I'm using this step times e to x minus f of x. Derivative of e to x is e to x. This function is a pleasure to differentiate. To differentiate it, we can just as well erase the prime. Divided by e to x squared. So what is this expression? How can you simplify?
You can factor out b to x.
I can do even more. So it's f of x times e to x minus f of x times e to x divided by e to x squared. What is it?
You just cancel out one of the differences from the denominator.
Okay. And what am I going to get?
F prime of x minus f of x over e.
F prime of x is the same as f of x. So here I already plugged it in.
So you're just gonna get 0 over e to the x.
Or, even simpler, 0. Yes. So you're taking a number, well, you're taking f of x times e to the power x and subtracting it itself. The result is 0. Then you divide 0 by some number, which is, by the way, not equal to 0. So you divide 0 by number, you get 0 still. Well, conclusion. Derivative of this function g is in fact 0 for any x. Now that's something strong. What can I say about the function for which the derivative is 0 at any point? Can you say further?
It's a straight line.
It's a straight line. Yes, the graph of this function is a straight line. The rate of change of this function at any point is 0. It means this function is never changing. So g of x is constant. G of x is c for any x. For some number c, this function is just this number for any value of x, never changing. Once again, the reason is because the rate of change of this function at any point is 0. So the function just never changes. But this means that f of x divided by e to the power x is this number c. So the function f of x was in fact c times e to the power x. So now we showed that any function for which the derivative is equal to the function is in fact of this form, a number times e to the power x. And once again, how we found this? Well, we started with the function with this property. We formed a new function, which was f of x divided by e to the power x. We found the derivative of this function using the quotient rule. Then we used this property to simplify this expression and get that the derivative is 0. And finally, we concluded that the function whose derivative is 0 must in fact be constant. That was the proof. Okay, so questions about this thing? Okay, so let me write the conclusion. F prime of x is f of x whenever f of x is a constant, it's e to the power x. Let me not repeat this calculation once again for slightly more general equation. just give you the answer. More generally, if you want to solve such an equation, a function whose derivative is not equal to the function itself but proportional to it, some number r times this function. This happens only for functions of this form. A number times e to the power r times x. So please remember this fact. We will see in a second why it's useful. So it's just a small generalization of what we actually computed, except, well, here I'm interested in function e raised to power not just x, but a number times x. And its derivative happens to be r times the function itself. Well, the reason I ask you to remember this fact is because this differential equation is extremely important. It appears over and over in different simple models of growth. Example. In year 2000, the population of the Earth was, let's say, 6 billion. If the population grows at the rate of 1% per year, what is the population years after the year 2000. So here's a problem that people who study demographics might be very interested in. We know a data point, population on the Earth in year 2000 happens to be about 6 billion. And we also know the dynamics of how the population grows. Turns out that population every year grows by 1%. It's not exactly the rate of change during the year, it's instantaneous rate of change at every point. It grows at a rate which is 1% per year. And the question is how to model this growth of population. Let's say, what is the population in year 2030? What is the population in year 2013? What is the population more generally t years after the date of measurement? Let's solve this. Solution. So first of all, we'll give a name to the quantity which I am interested in. Let's say P of t, so population at time t will be population t years after year 2000. So that's the quantity that we are interested in. What is the population t years after the year 2000? What do we know? Well, we know there are some things. We know one figure is this 6 billion. What is 6 billion in terms of p? P of 0, yes. So 0 years after the year 2000, the population is 6. Well, let me say that we measure it in millions. Let me not care the 9 zeros. Let me just measure everything in billions of people. So P of 0 is 6. Another thing, this 1% per year. So it's the rate of growth of population. What is it in terms of P? What is the rate of change of a function P in mathematical terms? The derivative, yes. So P prime of T, well, now what is it? P prime is just the rate of change. How many people are born during a period of time. Here we are given this amount as 1% of the population. So what is 1% of the population in terms of P?
0.01 times 6 billion.
Okay, that would be at year 2000. But this actually holds for whatever the population is. If we are in year, I don't know, 2100, the population might have grown to 12 billion. And then the 1% will be larger. So what is it?
T times 0.01. Or
Okay, not quite T, but rather you're getting there. So it's 0.01 stated to 1% of what?
T.
P of T, of the population. So in year 2000 it would have been 0.01 times 6 billion, but more generally at the moment T, it will be 0.01 times P of T. So this is population, this is 1% of population. And this rate of change of population. Don't have too much time. Okay, so we have this thing. The derivative of P is a number 0.01 times P itself. We go over here and we see that this is a differential equation which we know how to solve. Derivative of function is number times this function. Conclusion, P of T is in fact some number times e to the power 0.01 x. So this part was part of just modeling, translating whatever data we have in the problem into mathematical terms. This step is application of mathematical theory. We just spent 45 minutes developing this theory, and we found that this equation has such a solution. Now we can solve the question completely. So for now we have this P of T up to some number C. How to find this number C? Yeah?
You can plug in the 1.8
Yes, so we still haven't used this data. This data. So P of 0 is 6. On the other hand, P of 0 is C times e to the power 0.01 times, oh sorry, this was T. This was supposed T. My variable is T, it's not X. Times 0. Which is C times e to the power 0, e to the power 0 is 1. So C is in fact 6. Answer P of T is 6 times e to the power 0.01 times T. Now we can answer any questions of the form, what is the population going to be in year 2030? According to this model, 6 times 0.3. That is the answer. Okay, so questions about this problem. Alright, so we'll meet again on Friday and we'll discuss more of this and we'll start loading.